Whereas we want to look at an example of permutation test in R. And to begin with, unlike the standard bootstrap where samples are drawn with replacement, the permutation test is another resampling technique where samples are drawn without replacement. They are often applied as a non-parametric test of the general hypothesis H0 x equal to y versus the alternative x not equal to y, where x and y are independent samples from two unspecified distributions. Now, with a permutation test, the focus is always on the distributions for the two samples. We want to find out if the first distribution is the same as the second distribution. But with the standard bootstrapping way of hypothesis testing, we will have focus on the location parameter for the distributions. Maybe we would like to say test if the mean for the first distribution is the same as the mean for the second distribution, right? But in here with permutation test, the focus is just on the distribution for the two samples, right? And one of the non-parametric tests that we can use to address this kind of hypothesis is the Kolmogorov-Smirnov test, right? The Kolmogorov-Smirnov test is basically the maximum absolute difference between the empirical cumulative distribution functions of the two samples. That's basically what we're going to use to address this kind of hypothesis. Even though we have other tests like the Kramer-Von-Mises test which can be used, but we're going to just limit ourselves to Kolmogorov-Smirnov test in this tutorial, right? So now let's look at the steps involved for performing permutation test. First, we compute the observed test statistic denoting D0. The next step is to create a pool sample Z, where Z is the order set of the two independent random samples X and Y respectively. Then for each replicate index R starting from 1 to big R, we draw a resample of size NX from Z without replacement to represent X. We use the remaining observations from Z to represent Y. Then we compute the test statistic. This test statistic is basically the test statistics for each replicate, right? Now, if large values of the observed test statistics support the alternative, we are going to compute the empirical P value defined below. This is the formula we're going to use to compute the empirical P value. For a two-tailed test, we are going to multiply the empirical P value by 2. The last step is to reject the null hypothesis at a level of significance if the empirical P value is less than or equal to the alpha level of significance, right? So let's quickly look at an example. The weights in grams are recorded for 6 groups of newly hatched chicks fed with 6 types of feed supplements from the chick weight data in R. Test whether the distribution of chick weight for the soybean and linseed groups differ at 5% level of significance. So we want to use the permutation test to find out if the distribution of chick weight for the soybean is basically the same as the distribution of weight for the linseed group, right? So let's quickly jump into R. Alright, so in here we can use the data command, this code of line, to get the different data sets or types in R, the inbuilt data in R. Let's run this. So I want to use this just to see most of the different data sets in R, right? So here we have different inbuilt data in R, but we want to focus on the chick weight data, right? That's the weight versus age of chicks on different diets. So let's go back and look at view our chick weight data. So I want to view data sets. Let's run this. So we have 2 variables, weight and feed, and we have different types of feed. We have horse bean, we have linseed, we have soya bean, we have meat, sunflower, meat meal, and we have casein, right? So let's explore more. Let's look at the structure of our data set. Chick weight. So this is structure of data sets. So we have 71 observations of 2 variables, and these are the 2 variables, weight and feed. We can basically attach this data set so that 8 variables can be accessible in R, right? So we attach the data set. Then the next step is to get a graphical summary of the data set. So I'm going to use the box plot. Right, so check weight. No, this just gives me for the 2 variables. I want to get for each want to get a different types of feed for each weight, right? So let me use this formula. Check weight. Yep, this should be good. Yeah, so let's look at it. So if you look at the distribution of weight for the different types of feed, we can see that it seems to be different. But if we concentrate or focus on the linseed and the soybean, that's basically what we want to look at. If the distribution of weight for this variable is the same as the distribution of weight in here, you can see this seems to be symmetric, this seems to be skewed, but we want to find out, test the hypothesis to see if they are the same or they differ. Alright, so let's continue. So once we have this, let's assign the check weight data set to some defined objects. So I want to assign the linseed to the variable x or the object x, so weight, right? Feed, then we can say linseed. So this is the linseed variable, right? We are denoting it as x. Let me copy this, paste, change this to y. Feed, that's, we want to get a soybean variable, soybean. So let me change this to soybean. So let me run this too. Alright, so we have them installed here. The linseed is 12 values, the soybean we have 14 values, right? Now we can get our first step. We can compute the first step for the permutation test. Is to compute the observed test statistic D naught, right? Sorry. So compute the statistic from the observed samples. So I'm gonna denote this D naught and say ks.test. That's the Kolmogorov of test. We have x and y, linseed and soybean. Alternative is going to be two-sided, right? Two-tier test, two dot-sided. Then we are interested in a statistic, right? So I want to see the results, so let me run this too. So here we go, we have the test statistic is also stored here for us. So 0.29, right? So what conclusion can we draw from these observed samples? Let's get a corresponding P value. I'm gonna copy these two lines and paste. Change this to P val. P val P dot value, yeah. So this will help me get a P value. Let me run this. So here we go, we have 0.616. If you compare this to alpha level of 0.05, we fail to reject H naught and conclude that the distribution of weight for linseed is basically the same as soybean. But the question is, are we going to draw the same conclusion if we have to repeat this experiment 1000 times? This is where I want to set up the pseudocode for permutation test. So pseudocode for permutation test, right? Alright, so I think we are done with the first step. We now want to start from the second step. So we want to create a pool sample Z, where Z is the order set of the two independent random samples. So I'm gonna say Z should be, I'm gonna use a sort in order to order it X and Y. So I'm just getting the pool sample, right? So I'm gonna run this. We have it's not going to be 26. Yes, if you add this 2, you're going to get 26. So I'm going to get certain indices for this pool sample. I'm going to say 1 to 26. So indices for pooled samples, or not for the pool sample. Yeah, so this is basically going to help us to draw the samples without replacement, right? So we need this. Then we can get a replicate, right? So R1000, that's going to be the number of replicates. Then we have to set a container to store the statistic for each replicate. So I'm going to say d.star and say numeric, right? Numeric of R. Yeah, so empty vector to store test statistic for each replicate, right? So we can now apply the for loop. So we are almost here. We want to draw a sample of size nx from z without replacement to represent the first variable. Then we use the remaining for the second variable, right? And compute the test statistics for each replicate. So let's go back. So for index r in 1 to r, I want to draw a resample of size 12 from z to represent linseed, right? So I'm gonna say use this for a sample without replacement. Sample from k, size should be 12, that's the linseed is 12. Then replace is now false. So sample without replacement, right? So let's continue. Once we have this, so the first variable is x, right? That's the linseed, but I want to denote it as x1 in here for the for loop. So I'm gonna say z sample from z k, right? So that's the linseed values. Then I'm gonna say use the remaining observations from z to represent soybean, right? That's the second variable. So I'm just gonna say y1 and say z minus k, right? So the remaining, since it's without replacement, if it samples 12 from k, it will be left with 14, and the 14 will be used in here, right? So this is going to be the soybean values or replicates, right? Then we can store the test statistic for each replicate in d.star. That's the container that we've created. So I'm gonna say d.star r, yeah, that's the index for the replicate. Then k s.test, say x1 y1, then sample, alternative, this is going to be two-sided, two-dot-sided, right? So two-dot-sided. Then we need a statistic, right? So we should be good to go. So let's run this looping. Yep. Let's run this. Oh, I've changed the z to small z, so this should be big Z, capital Z, Z, yep, because I'm using capital Z here, yeah. So let's rerun this. Alright, so you're good to go. These are just warning message as we encountered when we were trying to use the chromogram self-test. Yeah, so it's trying to say that anytime you have anytime we have paired or ties, we are not going to get an exact p-value, but we are going to get approximate p-value. So that those are the warnings, right? So from in here, let's continue. We can then get the empirical p value, right? So I want to compute the empirical p value. So I'm gonna say p dot val, or use pv for that, and say we are going to sum, right? So I'm gonna 1 plus sum d dot star, right? Sum d dot star greater than or equal to greater than or equal to d naught. Then we divide the whole of that by r plus 1, right? So let's run this. Then let's see pv, right? But this is just for 2 tail to multiply by that, right? So let's multiply it by 2. So here we go. So if you look at the p-value compared to alpha level of significance, we are basically going to draw the same conclusion, right? Here too, we fail to reject, meaning that you have to perform the experiment 1,000 times or many times. You are going to end up drawing the same conclusion. You are going to fail to reject H naught and say that the distribution of weight for linseed is basically the same as the distribution of weight for soybean. So this is basically how to perform permutation test for 2 samples, right, in R. So I think this you find this very pretty well understandable, right? So I think we are good to go, right? So please, if you found value in this video, I think don't forget to subscribe if you haven't, and also turn on the notification to get more updates, right? So thank you for watching.